Hello, welcome to the pandemic edition of Sub0. This talk is on something that we've been working on quite recently. We're still working on it a little bit. And I hope it will illuminate some of the issues and questions that you might have when trying to get your chain from something that is functional and works and has a test net and that you're generally happy with in terms of feature set, but is perhaps not going to stand up against sort of real world attackers. So what are weights? Weights are a solution to the problem of a denial of service. So, I mean, a blockchain is a fundamentally public service, right? It's a service that will generally, at least in sort of our world of sort of cryptocurrency and permissionless systems, will be maintained by public nodes, validators, if you like. And it's also one that we expect the public to be able to interact with, so use, basically, send transactions to, transfer funds, do whatever it is that the blockchain is meant to, whatever service it is that the blockchain is meant to provide. Now, blockchains have limited resources. They can't do everything for everyone all the time. Bitcoins increase the size of the presentation. I'm not sure I can. I'll resize the window. Maybe that helps. So yeah, blockchains are fundamentally public things. They're maintained and they're used by members of the public, and it's not the case that they can sort of do everything for everyone all the time. So they need to. We need to ensure that different people can use basically that our resources that we have on the blockchain are able to be used in some sort of fair way that doesn't overload those that have to maintain the blockchain, but also doesn't underwhelm those who want to use the blockchain. So if we look at like the specific people, the specific sets of groups of economic actors, we have two broad groups: the full nodes and the block producers. So the full nodes are those that are just trying to keep up with a network. They're our, in some sense, our ecosystem users, right? They're the people that either are sort of individuals running the blockchain on their local machine. Maybe they're running a light client and they're connecting to a full node. But they're broadly speaking the sort of end users. They may also be infrastructure providers, block explorers, who knows what else, but they're the ones, they're not producing anything, they're just sort of reading the chain. But nonetheless, they have to be able to keep up with it. They have to be able to verify it to make sure what they're seeing is correct. And so there is a computational cost to this that goes up as more work is done on the chain. Now, block producers are the other half. They're the ones that are actually creating new blocks. And these guys sort of need protecting a little bit as well, because it's important that when a new transaction comes in from the public, that they kind of know that they will sort of get paid for it in a pro rata sense, according to the cost that it will take to execute it for them. So weight helps us solve both of these issues with protecting our economic actors. So what precisely is weight? In some sense, it's a property of a subroutine, right? So it's some bit of code that executes. Well, it's a property of that code. Specifically, it's something that we say extrinsics or transactions. Extrinsics being the general term, transactions being extrinsics that, broadly speaking, come from users. Broadly speaking, are signed and as such de facto validatable. These extrinsics and also the top level hooks that you might be familiar with already, on initialize and on finalize, are two of them. There's also a third, on runtime upgrade, that you probably haven't used, but yeah, there aren't many of them. Now, these things take time in a block, right? And if they take too much time, then it means there's not as much time. Well, if they take more time, it means there's less time for other things. So we have to account for this. And that's really, weight is our means of accounting for it. Yeah. So it's a unit of account. In addition to it being a property of these functions, it's also a property. The property is associated also with the arguments that those functions take, which means some arguments might result in our function executing with a lower weight. Other arguments might result in our function executing with a higher weight. So when we calculate the weight of a function, we must also do so with respect to the specific arguments that it's going to be given. Now, some arguments might not have any effect on the weight, but the problem is that some arguments do, and we don't know which ones are which. So weight must be computed, broadly speaking, as a function of all of its arguments. Now, the weight of a function, or an extrinsic or a dispatch call, whatever you want to call these things, dispatch call is really at the lower level, what we say. It may depend upon the state of the chain, right? Upon some element of storage. Might be that there's lots of items in storage, and the function, the dispatch call or the oninitialize call, needs to go through every item, in which case it's probably going to be linear with the number of items. Now we then have to say, well, the weight must vary with the number of items, and that's problematic because determining a particular, like reading the state of a blockchain, is not a cheap operation. Going to the database is something that we want to do as minimally as possible, at least until it's clear that the transaction is being paid for. At the point where we're calculating the weight, you must remember it hasn't yet been paid for. Like, we can't pay for it until we know how much to pay. We know only how much to pay once we know the weight. There is a workaround. I'll discuss that later on. Okay, so specifically, what is weight? Weight's an indication of how long, how much time, marginal cost of time here, right? So it's not necessarily all bunched together in a single place. It's not necessarily the time taken for a particular function to happen, but rather how much longer the block will take to execute if some particular operation is included. Now, the operation we're basically limiting to a dispatch call happens. Usually this will happen via an extrinsic being applied, but it might also include things like on initialize, block initialization, on finalize, and a runtime upgrade. These are really the four things where we're concerned to know what the weight is. There is actually one other thing, two other things. These are lower level things. They're not really to do with what you as substrate chain creators need to worry about. But the other two things, for the sake of completeness, are the overall overhead of executing a block in general. So basically, all of the extra stuff that happens, mostly bookkeeping. But there's a few other bits. How much, and this would be a constant amount. Right, this isn't something that increases with the number of extrinsics or anything like that. What is that overhead? And also, what's the overhead of dispatching, of applying an extrinsic? Yeah. So this is to do with decoding the extrinsic, probably a transaction, and verifying that its signature is correct and all this sort of stuff. So those are sort of two additional things that need to be that need to have associated weights. But broadly speaking, there are, as far as sort of substrate chain authors are concerned, there's really only 4 things that for whose weights you need to be concerned about: dispatch call, dispatchable calls, on initialize, on finalize, and on runtime upgrade. Weight is linear, so twice as much weight should result in an operation taking twice as long, more or less. There's a lot of caveats to this, as I'll go into later, but broadly, that's what we're thinking about. So those caveats are: everyone's hardware is different, right? Different computers execute different things at different speeds. Hardware improves over time, which means even if we did have standard hardware for a particular time, it wouldn't really matter, because in a year's time, everyone's computers would have, well, many people's computers at least, would have been upgraded. So the standard hardware isn't really informative anymore. And of course, the software evolves as well. Rust compiler, the LLVM that it's based on, are constantly evolving. The libraries that we use, the operating systems that we use, and even the substrate node software is all evolving. It's generally evolving for the better. So broadly speaking, this is not a stable target, but nonetheless, we do need some way of mitigating this kind of denial of service attacks, these resource exhaustion attacks, and so we're sort of forced into this corner. So to give our units some ground, our weight units some grounding, we're going to link it to the time a specific operation takes, or the extra time taken, the marginal time taken, given specific benchmarking hardware. And as it happens, we'll probably also have specific software versions that we run on that specific hardware. So we'll be clear about kind of standard benchmarking methodology. We'll be clear about what it is that the times are reflecting, and it's these times that we'll be using to inform the weights. Now, so then you say, well, hold on, what is the unit then? Well, the unit is very simple. The unit is 1 picosecond, right, of marginal time required to execute the given operation on standard hardware with standard software. And this is what Substrate 2.0 and Polkadot, by extensions, weights will reflect, right? Now, of course, as time goes on, the software and the hardware is going to evolve. We'll probably introduce newer standards, who knows, maybe a year, 18 months down the line. And so the weights will be updated. But for now, weights are necessarily going to be a transient thing. And this is what they are for the moment, for this particular version. So Polkadot blocks, to talk about Polkadot for a second, will have a maximum total weight of 2 times 10 to the 12 picoseconds, or 2 seconds worth of weight, which means, roughly speaking, on standard hardware, all valid blocks will be able to be executed within a 2-second time period. Now, well, you say, well, hold on, Polkadot's going to have, what, 6-second block time? So why only 2 seconds? Well, there's all sorts of overheads. Aside from anything else, the blocks have to be transported around on the network. They have to be authored. So you have to execute the previous block, author the new one, and send it to everyone else and have them execute it all in time for the next block to be authored. So broadly speaking, we'd estimate roughly twice as much plus an extra second or so. So in our case, we're given the sort of extra margin, safety margin of 2 seconds. So it's like sort of 2 seconds to produce the block, 2 seconds for the importer to import the block, and 2 seconds to get it from being produced to being imported. And that's where our 6 seconds comes from. That's where, or vice versa, given our 6 seconds, that's where our 2-second time limit came from. You could be more conservative and reduce the maximum total weight to like 1 times 10 to the 12, and ensure that, broadly speaking, valid blocks will execute within 1 second. But that very much depends on how much you're going to push with your chain. So I think it's important to be clear about what weight is not, because there's some confusion. Weight is not a generic catch-all resource limitation system. It only works for the marginal time needed to execute some additional operation. That's it. It's nothing more than that. It doesn't try to govern the amount of memory used. It doesn't try to govern the amount of bytes used of a transaction, so basically the blockchain growth. And it doesn't try, very importantly, it doesn't try to manage the state growth or the storage growth of the blockchain. These have to be handled separately. Now, as it happens, memory usage is just a flat 1 gigabyte, right? So it's like it's specified in the, I think it's actually specified on chain, but it's also specified as a default parameter at the CLI. Basically, how many WebAssembly pages you want to provide. I think at the moment it's a gigabyte. The blockchain size or the growth of it is limited economically by having a fee, a per byte fee. This is specified actually in the system modules configuration. And the storage, the state growth size, at least in Polkadot and most of the standard palettes, is restricted by the need to for the users to place deposits down for any amount of storage that they use. So there is notable one being the existential deposit required for an account to exist. These have nothing to do with weights. Weights are simply to measure and eventually through measurement limit the amount of time it takes to import a block and by extension also to produce a block. Okay, so how do we specify weights? It's actually really, really easy. For dispatchables, we just have a little tag which we put above the dispatchable. So here's an example. The weight, as I mentioned, is measured in picoseconds on standard hardware. And here is an example function, my dispatchable. As you can see there, it takes an origin and it does some stuff. We don't really care what it does. And all dispatchables from here on in must have a weight tag. So that's placed above it, and it states what the weight will be for this function. It actually only states what the maximum weight will be, but if you don't do anything else, it will just use the maximum. So we'll assume for now we're not doing anything special. So it's the weight for this dispatchable is 100 million picoseconds on standard hardware. So on standard hardware, it should take approximately 100 microseconds to execute this dispatchable call. Now, that's not the total amount of weight that it will take to execute an extrinsic of this dispatchable call, because a transaction, I should say, of this dispatchable call, because of course a transaction has some additional stuff. It has to bump the nonce of the account sender. It has to reduce some balance. And it has to verify the signature of the transaction. And it has to do a few other little bits as well. But those are the main three. So it's not, the extrinsic won't be exactly this weight. It'll be a little bit more. There's a sort of an offset of the weight. But the bit that actually does the stuff that the user cares about, this particular call, we're saying takes 100 microseconds on standard hardware. Okay, easy enough. Weight equals 100 million. Now that value can also be an expression. So here's an example of an expression. And the expression can include actually several things. It can include any of the parameters, any of the arguments that your call is taking. And it can also include types from the configuration trait. So you can use the T double colon syntax in order to get at your configuration trait types, and from there you can pull out whatever you want to pull out. And it's also got statics and consts from your module or whatever you're importing. Now, technically, you can also use storage in here. So you can go to storage, but it's really not advised because it will mean storage is expensive, and this really needs to be cheap. If it's not cheap, then it means that block producers can potentially be DOSed by people sending transactions that they know will never actually be executable and therefore will never cost them anything on chain, but nonetheless take a lot of time, a lot of effort to work out what the weight is. And if they just pummel a block producer with these transactions, then it's problematic for the block producer because they're doing lots of database I/O, but they're not getting paid. So broadly speaking, we want to keep the weight expression to something minimal, something very easy, and certainly something that doesn't needlessly go off to the storage. Now, there are workarounds for this because there are instances where you really do need to understand what's happening in storage, because the fact of the matter is that your dispatch or your on-initialize hook or whatever will do different things depending on what's in storage, and some of those things will be very very time consuming and others may not. But for now, in this example, you can see I'm just using a parameter. So in this case, there's this active parameter, whatever. Maybe it means that the module is somehow active. It means that when this dispatch is called, it's going to do something heavy. So we just say, that should actually be, bollocks. Let me go back. Yeah. Okay, this is actually wrong. Sorry, these slides were done in the last hour or so. Actually, there should be a, let me see if I can edit it in place. Okay, cool. So what I'm going to do is just make sure that active, I think this is right. Yeah. Active equals let me just there we go. That's correct now. And present a view. Yeah. Okay. So you can see now that the parameter I'm passing in, active, is actually will alter the functionality of the dispatch. If it is active, it'll do something heavy. If it's not, it'll do something light. And so what we're doing is reflecting that with the weight. If it's active, the weight will be 100 million. But if it's not active, it'll just be 50 million. And that reflects how much time it's going to take. In principle, this means that self-heavy will take about 100 microseconds, and self-light will take only about 50 microseconds. Now, there'll be times where you know that a dispatchable call will take up to some amount of time, but it might take quite a lot less than that because there might be some things that happen. And it might only be clear that those things have happened, or it might be easiest by far less of a problem to work out whether those things have happened only by the end of the dispatch. So it might be that you have to sort of do some computation on state and figure out some stuff. And then depending on that stuff, maybe it's going to be very heavy, maybe it's going to be much lighter. And you don't really want to do all that stuff when calculating the weight. You really want to just sort of do it once it's done anyway. Well, we allow for that with refunds. So refunds basically allow you to give a bigger weight, a maximum weight, beyond that will be initially sort of charged for the system will initially assume that the dispatch is going to take, and then if it turns out it's not going to take that much, you can refund some of it. So this is why I say refund is kind of a little bit. I don't much like the word refund for this particular thing. I think a downwards correction is much. Refund sort of implies to me that it's gone somewhere and a bit of it's going to come back, and that's not really what's happening. It's really just a correction. and we're not refunding the amount that we give back is a corrected amount, not the amount that is being given back, right? We're not, although in this case it's the same because 50 is also 100 minus 50. But in principle, the figure that is here, the figure that's here is the corrected weight, not the amount that we're refunding. So yeah, what's happening here is we're saying, right, well, there's this is active state piece of state, and we want to see if our module is active. If it's not active, we'll just do something light, something that doesn't take very much, and we're going to correct the weight down to 50 million. So basically, we're saying in this particular branch, it only takes 50 microseconds on standard hardware to execute, and that's going to include, of course, the is active storage read, which could be significant. And if we don't do that, then we do the self-heavy thing. So that will just exit out normally, and therefore the full weight will be charged on that default branch. So how do we do this with block level hooks? That's dispatches, but block level hooks are a little different. These are not tagged. So our block level hooks, if you're not familiar with this terminology, I'm referring to on initialize. A pallet can specify what happens at the beginning of a block. On finalize, allowing a pallet to specify what happens at the end of the block. And there's also, as it happens, on runtime upgrade, which sort of behaves in a similar way. On finalize happens at the end. It's no use knowing only at the end of the block how long on finalize is going to take, how much weight it's going to take. We need to know at the beginning of the block, yeah? So on finalize itself doesn't do anything. It's not tagged, and it doesn't have any weight associated specifically with it. Instead, everything is done in on initialize. It doesn't make sense to tag on initialize with a weight in the same way we do with dispatch, because we don't really care. Like on initialize is going to be executed anyway. We don't really care knowing in advance how much weight it's going to take. Like it's not like we can choose not to execute it. So we don't bother tagging on initialize. We just return from on initialize what the weight is, which is to say its marginal cost, assuming we do the on initialize, which we have to do, so we're going to do it, but the marginal cost to the block import time of both on initialize and on finalize, both of them together. Now, most on finalize is a bit of a, you don't really want to be using on finalize because, it's, if you possibly can, you want to get stuff done at the beginning of the block. It's just generally cleaner. But there may be some instances where it's like actually quite important that you use on finalize. That's fine, but you have to include its weight in the on initialize weight. If it's something that is dependent on some state, then you kind of shit out a lot. You have to just assume it's the maximum, which is why I say best to do it on initialize. At this point, on finalize doesn't bother with refunds. There's not really any point. It's not like we can do anything after on finalize. So what could we possibly use the refunded weight for? Okay, so as I say, there's also this on runtime upgrade. This only happens, if you're not familiar with the API hook, this only gets called when the runtime has changed. Normally, you'll just use it for migrations. If it does anything, like obviously it has to return how much weight it's taken. So basically how much time on standard hardware it's taken. In this case, it's 100 billion, so that's 100 milliseconds to execute whenever it does execute this. If it's not an upgrade, if the runtime hasn't changed, then of course this figure won't be counted towards the block weight. Okay, so finally, I'm probably really close to being out of time, so I'll do this very quickly. How do we determine weights? Three things. Benchmarks. Yeah, that's a bit of a joke, but we do a lot of benchmarks. First two benchmarks are tree database read and write. We need to know how long it takes to access the database. We also benchmark how long an empty block takes and how long a no-op extrinsic takes. So basically how long it takes to dispatch an extrinsic. And then we go through the fairly painstaking process of benchmarking all the dispatches, which I'll very quickly describe the process of. Initially though, TreeDB read benchmarking, this is basically worst case time if we need to make a read from Merkle tree database, assuming we don't have it already in our overlay cache thing. So we have to go off to RocksDB, we have to do some cryptographic hashing and all that sort of stuff. We also need to profile benchmark the database write. This assumes that it's a dirty storage item, so we actually have to write it out and recalculate what the tree root would be. So those two things give specific numbers for database I/O. Then we have to we know our empty block and no-op extrinsic through doing basic benchmarking. These are always benchmarked, by the way, on our Wasmtine WebAssembly execution engine. They're not done on native. Native is substantially faster, but we can't be guaranteed that all validators will be running native all the time, and therefore we do it on a slightly slower, somewhat slower, I think about 50% of the speed, WebAssembly executor. Another reason for not being super over conservative in our block time limit, because most people who are keeping up to date with the chain at least will be running natively compiled code rather than the WebAssembly. Now, dispatchables and hooks must be analyzed to determine what elements of the state and arguments and potentially the configuration trait will affect the performance. This basically means reading through the code and figuring out what does this depend on. Classic computer science complexity analysis. Generally, things should be linear at most. Log better, obviously, but not super linear. If you've got super linear stuff happening that is unconstrained, like that basically any member of the public can execute, then you probably need to refactor your code. We profile the I/O accesses. So because when we benchmarking, we do so on a purely memory DB. We remove RocksDB, we remove all that tree stuff from the equation. We just do it with a memory DB, basically just an overlay, so super fast. But we do catch all of the times that we access the I/O specifically for unique reads or writes, and these are the ones that we eventually multiply up with our tree DB benchmarks to get our final weights. Once we've done the analysis and the I/O profiling, then we measure the non-I/O time required for the operation to complete, which basically just means, as I say, doing it on a memory DB backend. And palettes will generally tend to come with a benchmarking.rs file that contains all the logic that does all this stuff. Substrate can then be run in a mode that allows this to be executed under the appropriate Wasmtine basic database and database pre-initialization and so on. There is a macro benchmarks exclamation that allows us to very quickly run benchmarks across multiple factors and figure out what the timing is. I'm not going to go into this macro. I don't have nearly enough time, but it is there and it's relatively easy. So we can combine everything. We run Substrate in a special mode. It reports the base time taken for each of the things that we're benchmarking, as well as the marginal time taken for each of the factors that we've named. Here's an example for block execution timing. So this is this top one is for no-ops. The bottom one is for basic transfers. You can see that it's a no-op. 1,000 no-ops takes around 350 milliseconds, so that's about 350 microseconds per extrinsic extrinsic dispatch. Here's another example of some graphs. This is for the transfer extrinsic. You can see that our two factors that we've identified, the user seeds are basically one of a number of randomized seeds of the accounts that we're transferring between, and the number of existential deposits, so the number of accounts that exist in the system. It's actually constant across both of these factors, which is a good indication. We knew that it was constant, but we wanted to make sure. Here's an example of one that's linear. It's not constant. You can see a basic incline here. This is for democracy palettes propose extrinsic, and as the number of proposals gets bigger, the number of proposals that pre-exist on the chain, then the time it takes to make a new proposal goes up a little bit. This is basically down to decoding and re-encoding that is needed for appending. So we can combine everything. I think I'm on to the last few slides now. We get these kinds of weights. So weight is 120 million in this particular example, plus the this TDB weight. TDB weight is given to every configuration trait via the system configuration trait. It's a indicator of how long a database read and a database write will take in weight. In this case, what we do is we say, well, we have 120 microseconds on standard hardware of computation time, and then we also know that we read from one unique item from the tree, and we write two unique items back into the tree. And that is enough to explain to the to Substrate basically how much effort it takes to do your my dispatch call. From that, Substrate can ensure that your block producers don't produce oversized blocks, and your users will always be able to keep up with your chain. Here's another example. They may be dependent upon factors. In this case, we've got items, which is a VEC of U32. So it's going to, maybe the more items, the more work needs to be done. In this case, so it's 20 million or 20 microseconds on standard hardware, plus the number of items that we're passing into my dispatch multiplied by 1.2 microseconds on standard hardware. And then we say, well, we also have a bunch of reads and writes. We're going to read the number of items plus one, and we're going to write always two unique items. And that, again, it's a little bit more complex, but it's enough to tell Substrate exactly what it should be, how much it should be limiting users doing these transactions. Finally, two ways of mitigating the issue of your dispatch or on initialized call being dependent upon state, or specifically your dispatch call being dependent upon state. One of them is by using state hints. So here's an example. Here's the previous example with the items. But instead of the items being passed in as a function, as a VEC, we assume that the items are already in storage. Now this is problematic because, as I said before, we can't look at read the storage before we know the weight, right? Before we actually enter the dispatch call, it's too much effort on the part of the block producer to be doing this stuff before they know they're going to get paid. So what we do is we say, well, you have to pass in the correct value for the number of items in the state actually as a parameter to the function. And if it's wrong, then the function will be a no-op and you've lost your money, right? So that's very easy economic mitigation. And if it's right, then we continue, and we continue knowing that we charge the correct amount of weight. How do we know we charge the correct amount of weight? Well, because we know that the items hint is correct. We just checked it, and we know that we charged an amount of weight according to the items hint. And then so we look at the weight there, and you can see, well, it's 20 milliseconds, 20 microseconds of standard hardware, plus the items times 1.2 microseconds each, and then the reads and writes according to the items as well. Now that will only work, that's only the valid weight if items is correct, if they, for whatever reason, passed in the correct number of items according to how much is actually in state. But if we read this code, we know that we will bail out if items is not the real number of items in the state. So that's state hints. That's what basically you need to do if your dispatch weight is dependent upon state. There is an alternative, which is limiting and refunds. Now, this is only applicable when you can specify, for a fact that there is a maximum amount of work that could possibly need to be done. So basically, when your state is limited in some way. In this case, we've got this max items constant, and we're going to, we were asserting here that the real number of items is less than or equal to the max items. Now, of course, whatever is going to affect item count and the number of items in the state needs also to respect max items. We really don't. I only put the assert in there as something illustrative. This is not how we would normally limit the number of items, but nonetheless, you get the idea. The number of items in state can be at most max items, and therefore what we're doing is we're charging the maximum possible weight that we could charge. I wouldn't expect max items to be very large here, maybe at 10 or possibly 100. But if it's too large, then it means that users are going to be, they're going to have to pay vast amounts of tokens, only to be refunded later on, presumably. Generally, this only works where the max is relatively small. But there we are. So we've got the weight, the max items times our per item cost, and then the reads and writes of the max items. And then what we do is we go through, we make sure that it is actually we go through, we do our thing, and we adjust the weight to become to the sort of real value, or the value that it should be if once we now know the real items. Now we can do this because we're in the dispatch itself. It's perfectly reasonable to be reading storage within the dispatch. That storage read will already have been paid for by virtue of this base weight, this 20 million of base weight. Or presumably actually not even that, but rather the reads and writes. So the one in this case would presumably refer to the item count read there. And so, our correction is very simple. It's exactly the same as the weight function, but with real items substituted in for max items. Okay, that is the end of the talk. Thanks for your attention. I'm sorry it went over a little bit. Cool. Cheers.